This is part 3 of lecture 4.4, one-to-one and onto functions. In this video, we will consider functions which are both one-to-one and onto. Given a function f from a set A to a set B, f is said to be bijective or a bijection or a one-to-one correspondence if and only if f is both one-to-one and onto B. It follows that f is a bijection from A to B if and only if, for any object y in B, y has both at most one pre-image under f and at least one pre-image under f. That is, for any y in B, y has exactly one pre-image under f. We will sometimes use the following notation to denote that the function f from A to B is onto B. Here is a Venn diagram illustrating a bijective function. Observe that in a bijection, each element in the set A corresponds to exactly one element in the set B, and each element in the set B corresponds to exactly one element in the set A. The two functions at the right are not bijections because they are not surjective. The function at the lower left is not a bijection because it is not injective. For any non-empty set A, the identity relation on A is a bijection from A to A. This is because we showed in lecture 4.4 part 1 that I subscript A is an injection, and in lecture 4.4 part 2 that I subscript A is a surjection. Also, the empty relation is a bijection from the empty set to the empty set. This also follows from our result in lecture 4.4 part 1 that the empty relation is an injection, and in lecture 4.4 part 2 that the empty relation is a surjection. Consider the function f consisting of all ordered pairs xy of real numbers, satisfying the equation x plus y equals x times y. Then f is a bijection from the set of real numbers not equal to 1 to the set of real numbers not equal to 1. This follows immediately from two previous results, namely, example 1 in lecture 4.4 part 1, which showed that f is one-to-one, and example 1 in lecture 4.4 part 2, which showed that f is onto the set of real numbers not equal to 1. Consider the function g consisting of all ordered pairs xy of real numbers, satisfying the equation y equals x squared. Then g is not a bijection from the set of real numbers to the set of real numbers. Indeed, we showed in example 2, lecture 4.4, part 1, that g is not one-to-one. And in example 2, lecture 4.4, part 2, that g is not onto R. Consider the function g1 consisting of all ordered pairs xy, where x is a real number and y is a non-negative real number, satisfying the equation y equals x squared. Then g1 is not a bijection from the set of real numbers to the set of non-negative real numbers. Indeed, g1 is onto the set of non-negative real numbers, since the range of g1, which consists of all numbers x squared for every real number x, is equal to the set of all non-negative real numbers. However, g1 is not one-to-one, since, for instance, g1 of 1 is equal to 1 squared, which is equal to 1, which is equal to negative 1 squared, which is equal to G1 of -1. So 1 and -1 have the same image under G1, but 1 is not equal to -1. Therefore, G1 is not 1-to-1. Since G1 is not 1-to-1, it follows that G1 is not a bijection, even if G1 is onto the set of non-negative real numbers. Consider the function G2 consisting of all ordered pairs xy, where x is a non-negative real number and y is a real number, satisfying the equation y equals x squared. Then G2 is not a bijection from the set of non-negative real numbers to the set of real numbers. Indeed, G2 is 1-to-1 since for any non-negative real numbers x1 and x2, G of x1, G2 of x1 equals G2 of x2 implies that x1 squared equals x2 squared, which in turn implies that the absolute value of x1 equals the absolute value of x2. Since x1 and x2 are both non-negative, this means that x1 equals x2. However, G2 is not onto since the range of G2 is the set of all non-negative real numbers, which is not equal to the set of real numbers. Observe that G2 is a subset of the function G in a previous example. In particular, G2 consists of all ordered pairs in G whose first coordinate is non-negative. We say that G2 is the restriction of the function G to the set of non-negative real numbers. In general, let f be a function from a set A to a set B. Let C be a proper subset of A. Let D be a set containing A as a proper subset, and let E be a set containing B. The restriction of f to C is the function consisting of all ordered pairs xy in F such that x is in C. An extension of f to D is a function G from D to E such that the restriction of G to A is the function f. Consider the function G3 consisting of all ordered pairs xy of non-negative real numbers, satisfying the equation y equals x squared. Then G3 is a bijection from the set of non-negative real numbers to the set of non-negative real numbers. Indeed, we can show that G3 is 1-to-1 by the same argument used for G2 in example 4. And G3 is onto the set of non-negative real numbers since the range of G3 is the set of non-negative real numbers. Since G3 is both 1-to-1 and onto, it is a bijection from the set of non-negative real numbers to the set of non-negative real numbers. Observe that G3 is the restriction of the function G1 of example 3 to the set of non-negative real numbers. This result describes a property of the inverse relation of a bijection. In general, if F is a bijection from a set A to a set B, then its inverse is a bijection from B to A. Recall that the inverse of F is a function from the range of F to the domain of F, to the domain A of F, if and only if F is 1-to-1. To prove the result, assume first that F is a bijection from A to B. We need to show that F inverse is a function from B to A, and that F inverse is 1-to-1 and on to A. Since F is a 1-to-1 function, its inverse is a function from the range of f to a. This follows immediately from the result quoted above. Since f is a bijection, it is onto B. So the range of f is equal to B. So f inverse is a function from B to A. It remains to show that f inverse is 1-to-1 and onto A. To show that f is 1-to-1, we will again use the result quoted above. But this time, we will replace f in the result by f inverse. Since the inverse of f inverse is f, and f is a function from the range of f inverse to B, it follows from the result above that f inverse is 1-to-1. Finally, we show that f inverse is onto A. Since the range of f inverse is equal to the domain of f, which is equal to A, f inverse is onto A. This completes the proof of the theorem. This result describes a property of the composition of two bijections. If f is a bijection from a set A to a set B, and G is a bijection from the set B to a set C, then GF is a bijection from the set A to the set C. To prove this, assume that F is a bijection from the set A to the set B, and G is a bijection from the set B to the set C. Then both F and G are 1-to-1 functions. So by a result in lecture 4.4 part 1, the composite function GF is also 1-to-1. Also, F is onto B and G is onto C. So by another result in lecture 4.4 part 2, the composite function GF is onto C. Therefore, GF is a bijection from A to C, and the theorem is proved. You have now come to the end of lecture 4.4 part 3. Before you proceed to lecture 4.5, you are strongly encouraged to do the exercises given at the end of these slides. Thank you for your attention.